Introduction. Ravi, can you please open the window? Let some fresh air come into the room.
Sure, Father.
Father, when the sunlight comes from the window, why are the dust particles visible? Because air is a colloid, as it carries dust particles. These dust particles scatter the light. They have large size and are visible to naked eye. These particles seem to be floating zigzag in the air. This phenomenon is also known as Tyndall effect.
Okay, Father. I got the answer of my question. And I want to know more about this.
Son, to know more about this, you have to explore surface chemistry. Students, today we will study more about the surface chemistry. Objectives. At the end of this lesson, you will be able to define surface chemistry, understand mechanism of adsorption, classify adsorption, know about applications of adsorption, define and classify catalysis, analyze mechanism of enzyme catalysis, define and classify colloids, know the methods for preparation of colloids, explain properties of colloidal solution, define Tyndall effect and electrophoresis, define emulsions, know about applications of colloids. Definition. Surface chemistry is that branch of physical chemistry which deals with the study of the phenomena occurring at the interface, that is, the boundary separating two bulk phases. Solid-solid, solid-liquid interfaces are known. As gases are completely miscible, they do not form any interfaces. Interface is only a few molecules thick, but the area is dependent on the particle size of the bulk phases. Adsorption. The phenomenon of attracting and retaining the molecules of a substance on the surface, or a liquid or solid, leading to a higher concentration on the surface in comparison to the bulk, is called adsorption. For example, when oxygen gas is taken in a closed vessel containing powdered charcoal, then the pressure inside the enclosed vessel decreases. This is due to adsorption of the gas molecules on the surface of charcoal. The substance accumulating at the surface of the solid during adsorption is called adsorbate. The surface on which adsorption occurs is called adsorbent. Adsorption and absorption. The phenomenon in which a substance is uniformly distributed throughout the bulk is known as absorption. It is the penetration of the substance through the surface into the bulk of the solid. For example, when a sponge is dipped in a liquid, it absorbs some molecules of liquid. Let's make some important differences between adsorption and absorption. Adsorption involves unequal distribution of the molecular species in bulk and at the surface, whereas absorption involves uniform distribution of the molecular species throughout the bulk. Adsorption is rapid in the beginning and slows down near the equilibrium, whereas absorption occurs at a uniform rate. Adsorption is a surface phenomenon, whereas absorption occurs throughout the body of material. Sorption and desorption. Sorption. Sometimes the adsorbate dissolves into adsorbent. Initially, the adsorbate appears on the surface of adsorbent and later passes into the body of adsorbent. Thus, adsorption changes into absorption. Simultaneous occurrence of absorption and adsorption is called sorption. Desorption. The process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption. Mechanism of adsorption. The amount of heat evolved when 1 mole of the adsorbate is adsorbed on adsorbent surface is called enthalpy of adsorption. Adsorption is always an exothermic process, and enthalpy change of adsorption is always negative. When adsorbate molecules are adsorbed on the surface of an adsorbent, their freedom of movement becomes restricted and hence entropy decreases. Adsorption is spontaneous. Therefore, at constant temperature and pressure, Gibbs free energy decreases. Delta G is equal to delta H minus T delta S. Types of adsorption. Depending upon the nature of forces existing between adsorbate molecules and adsorbent, the adsorption can be classified into 2 types: physical adsorption and chemical adsorption. Physical adsorption. If the forces of attraction existing between adsorbate and adsorbent are van der Waals forces, the adsorption is called physical adsorption. Since the forces existing between adsorbent and adsorbate are very weak, therefore, this type of adsorption can be easily reversed by heating or by decreasing the pressure. Chemical adsorption. If the forces of attraction existing between adsorbate particles and adsorbent are almost of the same strength as chemical bonds, the adsorption is called chemical adsorption. Since forces of attraction existing between adsorbent and adsorbate are very strong, therefore, this type of adsorption cannot be easily reversed. Comparison between physisorption and chemisorption. The important difference between physisorption and chemisorption are: low enthalpy of physisorption, usually of the order of -25 kJ per mole, whereas high enthalpy of chemisorption, usually of the order of -200 kJ per mole. In physisorption, forces of attraction are van der Waals forces, whereas in chemisorption, forces of attraction are chemical bond forces. Physisorption usually takes place at low temperature and decreases with increasing temperature, whereas chemisorption takes place at high temperature. Physisorption is reversible, whereas chemisorption is irreversible. Physisorption is related to the ease of liquefaction of the gas, whereas in chemisorption, the extent of adsorption is generally not related to liquefaction of the gas. Physisorption usually forms multimolecular layers on the adsorbent, whereas chemisorption usually forms monomolecular layers on the adsorbent. Physisorption does not require any activation energy, whereas chemisorption requires activation energy. Adsorption isotherm. The variation in the amount of gas adsorbed by the adsorbent with pressure at constant temperature can be expressed by a curve termed as adsorption isotherm. At low pressure, the graph is nearly straight and sloping. Hence, the extent of adsorption x upon m is directly proportional to the pressure of the gas. This can be expressed as x upon m is directly proportional to P raised to the power 1. At high pressure, saturation of the adsorbent surface occurs, and then amount of adsorption does not depend upon the pressure of the gas. This can be expressed as x upon m is directly proportional to P raised to the power 0. Freundlich isotherm. In the intermediate range of pressure, x upon m will depend upon P raised to the powers between unity and 0. This can be expressed as x upon m is directly proportional to P raised to the power 1 to 0, or x upon m is directly proportional to P raised to the power 1 upon n, where value of n is less than 1, or it can be written as x upon m is equal to k multiplied by P raised to the power 1 upon n. K and n are constant, whose value depends upon the nature of gas and the adsorbent solid at a particular temperature. Taking logarithm on both sides, we get log x upon m is equal to log k plus 1 upon n log P. The graph between log x upon m and log P is a straight line. The slope of the line is equal to 1 upon n, and the intercept on log x upon m axis will correspond to log k. Applications of adsorption. Gas masks. These contain activated charcoal or a mixture of adsorbents and are used for breathing in an atmosphere containing poisonous gases. Removing of coloring matter. Animal charcoal removes colors of solutions as coloring impurities are preferentially adsorbed on charcoal. For example, bone charcoal is used as decolorizer in sugar industry. Controlling humidity. Silica and alumina gels are used as adsorbent for removing moisture and controlling humidity. Adsorption indicators. Dyes like eosine and fluorescein are used as indicator in titrating bromide solution with AgNO3. Precipitate of silver halide has the property of adsorbing these dyes and thereby producing characteristic deep colors at the end point in the titration. In curing of diseases. A number of drugs kill the germs by getting adsorbed on them. Removal of hardness of water. Ion exchange resins are used for removal of hardness of water. Some other applications of adsorption. Heterogeneous catalysis. There are many gaseous reactions of industrial importance involving solid catalyst. Adsorption of reactants on solid surfaces increases rate of reaction. For example, manufacture of ammonia, sulfuric acid, and hydrogenation of oils. Chromatographic separation. Components of mixtures especially of organic compounds, can be separated and identified by chromatographic analysis, which is based upon adsorption phenomenon. For example, thin layer chromatography, paper chromatography, and gas-liquid chromatography. Froth flotation method. Pulverized ore is suspended in water containing some pine oil and a frothing agent. When air is blown into it, the ore particles are adsorbed on the air-oil interface and come to the surface in the form of froth. For example, sulfide ores are concentrated by this method. Separation of inert gases. Due to difference in the degree of adsorption of gases by charcoal at different temperatures, a mixture of inert gases can be separated by adsorption on coconut charcoal. Catalysis. A catalyst is a substance which influences the speed of a chemical reaction without itself undergoing any chemical change at the end of the reaction. This phenomenon is known as catalysis. For example, when potassium chlorate is heated in the temperature range of 653 to 873 Kelvin, it slowly decomposes to give dioxygen. But if a little manganese dioxide is added, the decomposition takes place in the temperature range of 473 to 633 Kelvin, and dioxygen is released at a much faster rate. A catalyst may increase or decrease the rate of a reaction. A catalyst which increases the rate of reaction is called a positive catalyst. For example, decomposition of KClO3 in presence of MnO2. A catalyst which decreases the rate of reaction is called a negative catalyst. For example, tetraethyl lead is added to petrol to prevent knocking of the engine. Types of catalysis. The catalysis reactions are of two types: homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis. When the reactants and the catalyst are in the same phase, it is called homogeneous catalysis. For example, oxidation of sulfur dioxide into sulfur trioxide in presence of nitric oxide in the lead chamber process for the manufacture of sulfuric acid. Reactants, sulfur dioxide and oxygen, and the catalyst, nitrous oxide, are all in the same gaseous phase. Heterogeneous catalysis. When the reactants and the catalyst are in the different phase, it is called heterogeneous catalysis. For example, manufacture of methanol from carbon monoxide and hydrogen using ZNO plus Cr2O3 as catalyst. Reactants are in gaseous phase and catalyst is in solid phase. Adsorption theory of heterogeneous catalysis. In heterogeneous catalysis, the catalytic activity is localized on the surface of the solid catalyst. Heterogeneous catalysis occurs through the following steps: diffusion of reactants to the surface of the catalyst, adsorption of reactants on the surface of the solid catalyst. The adsorbed reactant molecules undergo a chemical reaction to form an intermediate called activated complex. The activated complex then breaks to form the products. The products then dissociate from the catalyst surface, known as desorption. Diffusion of product molecules away from catalyst surface. Nature of solid catalyst. Metals, alloys of metals, metal oxides, metal sulfides, or mixture of these are generally used as solid catalyst. The two important aspects of solid catalysts are activity. The ability of a catalyst to accelerate the rate of a chemical reaction is called activity. These catalysts accelerate the rate of reactions to a very large extent, and in some cases, the rate of reaction becomes 10 raised to the power 10 times faster in the presence of a catalyst. For example, a mixture of pure H2 and O2 does not react, but in presence of catalyst platinum, they combine to form water and the reaction takes place with explosive violence. Selectivity. It is the ability of a catalyst to direct a reaction to yield a particular product. For example, carbon monoxide and hydrogen react to give different products in presence of different catalysts. Shape-selective catalysis by zeolites. The catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and product molecules is called shape-selective catalysis. Zeolites are good shape-selective catalysts because of their honeycomb-like structures. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminium atoms. The reactions taking place in zeolites depend upon the size and shape of reactant and product molecules as well as upon the pores and cavities of the zeolites. Zeolites are used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization. Enzyme catalysis. Enzymes are complex nitrogenous organic compounds which are produced in living cells of plants and animals. They are also known as biochemical catalysts because of their importance in biochemical processes. Almost all enzymes are complex protein molecules with high molecular mass. Enzymes are produced by living cells. A typical cell, on an average, contains about 3,000 different kinds of enzymes, each enzyme catalyzing a particular reaction. For example, conversion of milk into curd by lactobacilli enzyme present in curd.